Okay, good morning everybody. So let's see if we can finish the course today. Okay, so we discussed LP spaces last time. We were actually in the middle of it. So if you have a probability space omega fp, we talked about the space L0 of all real valued random variables determined or identified up to almost sure equality. So in this space, two random variables are considered the same if they are equal almost surely. And then we talked about subspaces of that. So LP is the space of random variables in L0 whose pth norms are finite. And on that space, this function is indeed a normed space. And it's even a complete normed space, meaning that it's a Banach space. Here P is between 1 and plus infinity. And we gave the definitions of those norms last time. Okay, so one thing about those norms is the proof of triangle inequality. So how can we make sure the norm of x plus y is less than the sum of the norms of x and y? Because we just assumed this last time. We didn't prove it. So today we will first start by proving that. And for that, we're going to start with some very well-known inequality called Jensen's inequality. So let's say you have a random vector whose expectation is whose expectation exists. So expectation exists, meaning that every component is indeed integrable. Okay, so it's not just existence but also the finiteness because we collect them in a vector. So let f be a function from Rn to R, okay? So we have the following relationship between the expected value of f of x and the f of the expected value of x. So we have this one when f is convex. So I want to give it for both cases. So when you just flip the signs, you get the inequality for the concave case. Okay. Usually it is stated for the convex case, but just the concave case is opposite because if you have a concave function, the negative of that is a convex function. So let's show it. So suppose f is convex. First of all, why is that measurable? Well, what can you say about a convex function on Rn with finite values? Optimization course, maybe you learned something about convex functions. So if you have a convex function on Rn with finite values, so there is no plus infinity, okay? What can you say about f? So convex functions are upper semi-continuous, and if you also have finiteness, you also have lower semi-continuity, so that the function is indeed continuous, right? So since f has finite values, it is well known that f must be continuous, hence measurable. And one more thing about convex functions is that you can write f, we may write f as a supremum over affine functions. Say f is the supremum of some fi's over a family of affine functions where each fi is affine. Okay. So this is also another fact from convex analysis. So if you have a function f, so its graph is something like that, which is a closed convex set, epigraph, let's say, then you can write it as a supremum over functions that are below it, right? A supremum over affine functions below f. So these are those fi's. And some of them really support this set. Namely, some of those functions really touch the epigraph of f. In that case, it is called a supporting hyperplane or supporting half space, right? Anyway, so if we have that, what is nice about an affine function is that it is a linear function plus some constant, right? So indeed, expectation works very well with affine functions, right? So when you take the expectation of that, or let's first look at this. So since this is a supremum over fi of x's, this is greater than each of those fi of x's, right? So if you take expectations, this is just fi of expected value of x because fi is affine. Fi is affine. So we have expected value of f of x is greater than fi of expected value of x for all I. If you take supremum over the right-hand side values, you get that it is just f of expected value. For the convex case, we get the inequality, right, as desired. And the concave case is just the negative of it. Just as a remark, a conditional version of that inequality exists. A conditional version also exists. So if x is integrable and so on, then you can have expected value of f of x given g is greater than f applied to the conditional expectation of x given g. This is almost surely because these are random variables now. Right? Let's say for f convex. And x is, let's say, in L1. Let's say just in one-dimensional case, okay? Okay, but so one can prove this inequality because we have the conditional versions of all the theorems about expectations, right? Dominated convergence theorem, monotone convergence theorem, and so on. And this is just one more theorem about expectations. So there is a conditional version of that, which can be shown by checking this inequality, okay? But we're more interested in corollaries of this inequality. So just take one nice convex function or concave function. This is going to give you an inequality, right? So if you pick f to be a special type of convex or concave function, you're going to get an inequality. And those inequalities are going to be very nice and useful. So let's start. So our aim is to come up with inequalities about LP spaces, okay? About LP spaces. So let's say we have, okay, we're going to list some inequalities, okay? So let PQ be in with 1 over P plus 1 over Q is 1 over R, okay? Then we have the following. The rth norm of LR norm of XY is less than the pth norm of X plus, times the qth norm of Y. I guess we allow for 1 as well. We just exclude infinities. Okay. So for the proof of that, we're going to look at the special case of Jensen's inequality, okay, for a concave function, okay. But let me first say that if this is plus infinity or this is plus infinity, then the inequality is trivial because the right-hand side just becomes plus infinity, which is always true. Then the inequality is trivial. So assume X is in LP and Y is in LQ. So here we have just things from L0, okay, one-dimensional random variables. So take f of u and v given as u to power r over p times v to power r over q. Okay. For positive numbers, and apply or note that f is a concave function. So if we take if we apply the inequality to f with the vector x comma y, okay, what do we get? So we have the less equal version here. So expected value of f applied to absolute value of x and absolute value of y, right? but we picked r over p, r over q, so I guess we need to take x to p and y to q, which is going to give us, so expected value of f of this random vector, it's going to be what? So x to power p times r over p, y to power q times r over q is less equal, now f of the expected value. So it's going to be expected value of x to p to power r over p and expected value of y to q to r over q. Okay. So what did we get? We need to, so this is just the rth power of x times y, right? To get the rth norm, all we have to do is to take its root, rth root. Take rth root to get xy rth norm is less equal. So if you take the rth root, this r is going to disappear, and you're going to get the LP norm of x and the LQ norm of y. Okay. So just a special case of Jensen's inequality. Okay. So number 2 is called Hölder's inequality, and it is a special case of the general inequality that we just stated, but with one extra value. So we're going to allow for, so let PQ be in 1 to plus infinity, including plus infinity, with 1 over P, 1 over Q equals 1. So we call P and Q conjugate exponents. So such pairs, P and Q, are quite important in many inequalities, not just in probability, but also in optimization and convex analysis, I guess. So in general, duality, because if you consider LP as a topological vector space, its topological dual space is the LQ space with that relation. Okay, 1 over P plus 1 over Q equals 1. Indeed, if you have P is 1, then you have Q is infinity. If you have P is 2, then Q is 2. So these are the special cases, okay? Special cases. So P equals 1 and Q equals plus infinity. And P equals 2 and Q equals 2. Anyway, so what is the result that we're going to state? Just a special case of this. So then we have the following. The L1 norm of x times y is less than the LP norm of x times LQ norm of y. Okay? So this is called Hölder's inequality. So for values that are not equal to plus infinity, this is just a special case of this inequality, right? Just take r equals 1. Just take r equals 1. So for the proof, if P and Q are finite, this is a special case of number 1 with r equals 1. So let's prove the case P equals 1 and Q equals plus infinity. So you have x times y is less than the absolute value of x times, just equals absolute value of x times absolute value of y, which is less than, we're going to look at the L infinity norm of y. So let me write it like this. So I keep x the same, but bound y by its upper bound, which holds almost surely. Remember that the L infinity norm gives you the upper bound of the absolute value of the function almost surely, okay? So it's okay if this upper bound is not satisfied on a null set, okay? So y is less than, so the absolute value of y is less than the L infinity norm of y almost surely, okay? So now that this is a constant, we can take expectations, okay? And we get the infinity norm of y times expected value of x. Okay? So this just means it's the L1 norm of xy, and it's the L1 norm of x. And the other case, p is infinity and q is 1, is symmetric. So one further special case of that has a separate name. It's called Cauchy-Schwarz inequality. So let me write it in the nicer form. Well, first let me write it as a special case. Okay, just a special case. P equals 2, Q equals 2, okay? But I can also write it as, so this simply says what? Expected value of x times y is less than the square root of expected value of x squared times expected value of y squared, right? And if you replace x by x minus expected value of x and y by y minus expected value of y, then this would become the covariance between x and y, alternative form. So the covariance of x and y is, in absolute value, is less equal the square root of the variance of x times variance of y. In other words, the product of the standard deviations of x and y. So for the proof, just replace x with x minus expected value of x and y with y minus expected value of y. And this case is just, this inequality is just a special case of Hölder with p equals 2, q equals 2. Okay. And I'd like to put it in a box. So sometimes we had issues with the finiteness of covariances and so on. For instance, when discussing Gaussian random vectors, okay? So for those, the issue was the finiteness of covariance between two components of a Gaussian vector. But we all know that in a Gaussian vector, every component is Gaussian. Therefore, every component has finite variance, right? So if this is finite and this is finite, then covariance must be finite. So covariance exists and it is finite. So if you have a random vector with finite variances on components, then you don't need to worry about the finiteness of the covariance matrix due to Cauchy-Schwarz inequality. Okay? So we just avoided discussing such details at that time, but now we have justification. Okay? So now no worries about finiteness of covariances in a Gaussian vector, for instance. It's a very famous inequality. And indeed, this is, maybe I should put it as a remark. So the correlation coefficient is defined as between x and y is defined as covariance xy divided by square root of variances, or product of the standard deviations. So, and we know that this is a number between -1 and 1. Why? Because of Cauchy-Schwarz inequality, right? This divided by those standard deviations is less than 1. Therefore, without the absolute values, this is a number between -1 and 1. Although covariance can be quite large, this is a scaled version, right? Always between -1 and 1. Anyway, we have a number 4 called Lyapunov inequality. Or Lyapunov's inequality. Okay, this is the order of norms. So if you have 1 less than r less than p less than plus infinity, then the rth norm is smaller than the pth norm. Okay, so if you have r less than 1, r less than p, then 1 over p is less than 1 over r, right? So you can find a q such that 1 over r is 1 over p plus 1 over q. Indeed, there is just a unique q. So now you can make it like the case of number 1, but you don't want the q part, so take y equals 1 in number 1. We get what? X times 1 rth norm is less than x pth norm times 1 qth norm. So this is just 1, right? So we get the inequality. So the consequence of this is that if r is less than p, so suppose we have r less than p, then x is in LP implies x is in LR, right? Because if this is finite, then this is finite. If the LP norm is finite, then the LR norm is finite. This means that we have, LP is a subset of LR. In particular, we have, so L infinity is the smallest one. So the larger the exponent, the smaller the space, right? So L infinity is the smallest one because these are just bounded, essentially bounded random variables. Then we have the square integrable ones. I'm skipping the values in between 2 and infinity. Then comes the integrable ones. And everything is a subset of L0, right? So does that make sense? If you have a bounded random variable, or essentially bounded random variable, it is integrable. Any power of that is also integrable, right? So L infinity is the smallest one, L0 is the largest one, and in between we have integrables, square integrables, etc., etc. So if something has finite variance, then it must also have finite mean, right? So if you're given finite variance assumption, you don't need to worry about finiteness of the mean, it is automatic. Okay? So if something is bounded, you have everything. If something is square integrable, it is also integrable, etc., etc. And a final one. Is the triangle inequality that we'd like to prove. So this is called Minkowski's inequality. So let p between 1 and plus infinity, then the p norm of x plus y is less than the sum of the p norms of x and y. So indeed, this is a triangle inequality for the norm, which finishes the proof that this LP, this norm is, the p norm is indeed a norm. So again, we're going to take a concave function and prove it as a corollary of Jensen's inequality. So again, we can just assume x is in LP and y is in LP, and take f of u and v as u to power 1 over p plus v to power 1 over p to power 1 over p, to power p. Okay, so I don't check that this is concave. So you can check it because these are just differentiable functions, so it is, you can just check it by derivatives, right? And then apply Jensen. So apply Jensen to u equals x to power p and v equals y to power p, I guess. So where is our Jensen? It's here, the concave version. So the expected value of f of this vector, let me write it this way, okay? Let's apply it to this vector, okay? So this gives us x to power p to power 1 over p plus y to power p to power 1 over p to this, I guess. This is less equal f of the expected value like this. Okay, this is the pth norm. This is the pth norm of y. So if we take a okay, this is also less than x plus y to power p, right? By triangle inequality for x plus y, because this is just x, absolute value of x plus absolute value of y, right? Sorry, with p here. Okay, also p is inside here. So if you take the pth root, so taking pth root gives just x plus y in LP, then norm of x, norm of y. So this means we are done. So we are done with the proof that this is a norm on LP for all p between 1 and infinity. Okay, so many inequalities. But this Minkowski is simply triangle inequality. Cauchy-Schwarz you might have seen in other places. I mean, it has many non-probabilistic forms as well, right? Because it's all about Jensen, and indeed, without the expectations, it is just the definition of concavity. Okay? I mean, if you take expectation as like just two probability, let's say you have a probability space with just 2 points, then your probabilities are like lambda and 1 minus lambda, which are the coefficients in the definition of convexity and concavity, right? So you can see the definition of convexity and concavity as a special case of this inequality. You know, you have lambda of f of x plus 1 minus lambda times f of y versus f of lambda x plus 1 minus lambda y. And this is just the generalized version of that. Okay. Okay, very good. So now we can actually get back to the convergence part. Okay. So back to convergence in LP. Okay. So let P be some exponent, okay, and let x, x1, x2 be real valued random variables. So we say that xn converges to x in LP if the convergence happens with respect to the norm, with respect to the LP norm, right? So the distance between xn and x goes to 0, and by distance I mean the LP norm of the difference. Okay? So it is nothing but a convergence in a metric space given by a norm. Okay? So it is just one of the special metrics that you can use in a course in analysis. Okay? Okay, so we can sometimes write the limit is x in LP. Okay. So let me begin with just the uniqueness of LP limits, because the limit should be unique, right? So if you have xn converges to x almost surely, xn converges to y almost surely, then x equals y almost surely. If you have xn converges to x in probability, xn converges to y in probability, then x equals y almost surely, right? We showed those. Now we should show if xn converges to x in LP, xn converges to y in LP, then x equals y almost surely, or they're just the same random variable in the sense of L0. The proof is just one line. Just look at the difference between x and y, the distance between x and y, and use triangle inequality to write it like this. Just squeeze an xn in between, right? This is just triangle inequality. And you know that this converges to 0, this converges to 0. This is what is given to you, right? So this means, indeed, the distance is just 0. And since this distance is just the expected value of x minus y raised to power p to power 1 over p, so this means this expectation is 0. This random variable must be 0 almost surely, which implies x equals y almost surely. Okay, so the LP limit is also unique, almost surely. Okay, another one. Now we're going to look at the relationship between the convergence in different LPs. Okay, so if you have r less than p, okay, then xn converges to x in LP implies xn converges to x in LR. For instance, if you have convergence in L2, this implies convergence in L1. If you have convergence in L infinity, this implies convergence in L1 or L2. Okay? And this simply comes from this Lyapunov's inequality, the relationship between different norms. So if you look at xn minus x in LR, this is less than xn minus x in LP. And if this converges to 0, which is the case here, then the other one must go to 0 by sandwich theorem. So there is nothing to show. Right? If the right-hand side goes to 0, the left-hand side must go to 0 as well. So in other words, we have convergence in L infinity implies convergence in all other LP spaces. And if you have convergence in L2, it implies convergence in L1. So this is the relationship between different LPs. Now, what is the relationship between this and convergence in probability? Okay? So it turns out that this implies, so in LP implies convergence in probability. Again, p is just between 1 and plus infinity, okay? And for the proof, we can just take p equals 1 because we know that this implies convergence in LP for smallest p because of this relationship, right? So it is enough to assume p equals 1. So convergence in L1 implies convergence in probability. That's what we're going to look at. So now what is the definition of convergence in probability? We just take epsilon and try to show that this probability goes to 0. So how can we say that? If we know that xn goes to x in L1, so how can we relate this with expected value of xn minus x? What is the relationship between the two? Do you remember any inequality bringing the two together? Markov's inequality, great. And it says what? This is less than this expectation divided by epsilon. Right? Markov's inequality. So we're done. And one can come up with so one can find a counterexample for the reverse. Okay. So in other words, right now we have convergence in the almost sure sense. So convergence almost surely implies convergence in probability. And this is also implied by convergence in, let's say, L infinity, which implies convergence in L2, which implies convergence in L1, which implies convergence in probability. So we have two lines, two streams getting to convergence in probability. And we're going to have one more concept in the next hour, which is convergence in distribution. But before doing that, I'd like to prove with you a very nice theorem, indeed one of the most important theorems in probability and also in statistics. Any guesses? What is the most important result in probability and statistics? That is one. That is for the next hour. What is the other one? Law of large numbers. So let's state law of large numbers. Okay. And try to prove it. Law of large numbers. Okay. So we're going to take IID random variables. So let x1, x2, etc. be IID, real valued random variables with finite common mean A and finite common variance B. Then we have the average of those numbers, x1 to xn, converges to the expected value of each in L2 in probability and almost surely. Okay, in three modes. Three modes. So the first two are called the weak law of large numbers. Law of large numbers, okay? And the almost sure one is called the strong law of large numbers. Okay? Let's prove the weak one first, and then the strong one we'll do in the second hour. So let Sn be the sum of xi's, okay? Just for notation, for convenience, let's just define the sum from 1 to n. So what do we look at? We look at Sn over n, whose expected value is just A, and whose variance is, well, you have n of those things, so the total variance is, sorry, Sn over n. So the total variance is just n times B divided by n squared, so it is B over n. Okay? And since the mean is A, so the square, expected value of the square is simply the variance of Sn over n, which is B over n, which converges to 0. So Sn over n goes to A in L2. In L2. Hence also in probability. You can also say in L1, right? So if we have in L2, we also have in L1 and also in probability. So this just proves the weak law of large numbers. For the strong one, we need to work harder. So we give a break now and work on that in the second hour.